Now it's my turn to show you around the geometry garden. My name is Escher, and I was a Dutch artist in the 20th century. Geometry was a constant source of inspiration for me. I'm a past master in the art of drawing fantastic tilings. Look at this self-portrait in a spherical mirror. One of my most famous drawings shows lizards drawn on a plane that managed to break out of the paper. Now, perched on high, they contemplate their previous existence as flat life. To prepare ourselves for life in 4 dimensions, we are going to use the ideas behind both my engraving and a little book published at the end of the 19th century by Edwin Abbott, an English clergyman, called Flatland. Let's try and explain to these flat beings, these creatures living trapped forever in a plane, what our everyday life in 3 dimensions is like. Let's imagine that one of these lizards manages to escape his miserable existence for a moment and climbs out and up onto a viewpoint looking down on his world. How would he explain to his fellow reptiles the existence of objects in 3 dimensions? As a first attempt, he could try to pass some 3-dimensional objects through his flat world. Here, for example, is a tetrahedron with its 4 faces, passing through the lizard's plane. The flat creatures see a green triangle appear suddenly, then gradually shrink away. This is all they see, since their senses are entirely restricted and they cannot perceive anything outside of their plane. Each time that a lizard sees these green polygons appear, change shape and disappear again, he might imagine the form of the object that has just crossed his plane. To see how hard it is to visualize the form of a geometric body from its cross sections, try to guess what is crossing through the plane now. A tetrahedron. And now, it was a cube. Of course, you have to remember that these lizards don't have the same perspective that we have. All they see is a sequence of polygons, and they'll have to develop an understanding of depth in order to fully appreciate the shape of the body. And now what? An octahedron with its 8 faces. And an icosahedron. It's a solid with 20 faces. And finally, the dodecahedron, 12 faces, 20 vertices and 30 edges. Now we're going to show you some cross sections, and only cross sections, and you have to guess the polyhedron hiding behind them. That was a tetrahedron. That was a cube. It's getting hard, isn't it? You see now that these creatures stuck in 2 dimensions have to develop good geometric intuition if they want to understand something of the 3rd dimension that we take for granted. We'll have just the same kind of problems to get a feeling for the 4th dimension. Here's a second method to explain polyhedra to our flat friends. Start by inflating a polyhedron so that the vertices and the edges are on the surface of a sphere. Then we stereographically project onto the plane of the lizards, so that our 2-dimensional friends may enjoy the spectacle. Of course, we can spin the sphere around, and with it our tetrahedron, just as we did before with the Earth. Let's take a look at the cube and see how many vertices, edges and faces it has. And now, here comes an octahedron. You see the 8 coloured faces. Look how the projections of the edges are arcs of circles. Now here comes an icosahedron. Its structure is more complicated, but it's not hard to understand even for the lizards. We can see 20 faces, 12 vertices and 30 edges. Can you count them all? Finally, here's a little geometric jewel, the dodecahedron. Now for some exercises. Let's take ourselves down into 2 dimensions and try to recognise the polyhedra from their stereographic projections. It's easy, isn't it? You can see the 4 faces, 6 edges and 4 vertices. There, it's a tetrahedron. Now, what's this one? 6 faces, each with 4 edges. That's right, it's a cube. That was harder, wasn't it? The faces are triangles. 5 edges start out at each vertex. There are a lot of faces, perhaps 20. It's an icosahedron. Well done. Let's look at the dodecahedron. Each face is a pentagon. If we count them, there are 12 faces. 3 edges start at each vertex. These 5 solids have always fascinated geometers. The Greek philosophers attributed a magical importance to them by associating to each of them one of the fundamental elements from which the world is formed. We call these figures the Platonic solids. So we agree then. It's not easy to get a feeling for the 3rd dimension when you're flat. There is more than one way to do this, but our stereographic projection appears to give a good idea of what's going on. Now we'll have to get ourselves ready for the 4th dimension. We're going to have to use our imagination.
My name is Ludwig Schleffli. I am a Swiss geometer. I lived during the 19th century, and I'm going to open the door to the 4th dimension for you. Even if I say so myself, I was a visionary. I was one of the very first to understand that spaces with a high number of dimensions really exist, and that their geometry can be studied. If flat creatures living in a plane can understand 3-dimensional polyhedra, then why shouldn't we understand polyhedra in dimension 4? One of my main achievements was to describe all regular polyhedra in dimension 4. What is the 4th dimension? A lot has been written on the subject. Science fiction writers never tire of talking about it. I'm going to explain things on the blackboard. You will see that this blackboard has a bit of magic about it. What's important is to prepare yourself to forget about the world which is familiar to us and to imagine a new world, that our eyes and our senses have no direct access to. We'll have to be smart, just like the lizards were before. I'm going to climb on the top of a viewpoint that unfortunately you cannot see, and I'll try to describe what I see from there. But before we begin, I'll draw a straight line on the board. Let me just mark the origin here. Each point on this line can be located by its distance from the origin, with a minus sign if it is on the left, and a plus sign if it is on the right. Usually the number is denoted by X and is called the abscissa. Since the position of a point on a line can be described by a single number, we say that the line has dimension 1. Now, I draw a second axis perpendicular to the first one. Each point in the blackboard plane is now completely described by two numbers, usually denoted X and Y, the abscissa and the ordinate. The plane has dimension 2. If you had to explain to some being living on a line what it is to be a point in the plane that is unknown to him, you could simply say, a point in the plane is just a pair of numbers. Let's go to the third dimension. The chalk now writes in the air and draws a third axis perpendicular to the two previous ones. A point in space is described by three numbers, X, Y, and Z. One could say to the reptiles that are curious to know about our world, a point in space is just three numbers. Let's go to the fourth dimension. One could try and draw a fourth axis, perpendicular to the others, but that's impossible. So we have to do something else instead. Of course, we might just say that a point in the fourth dimension is nothing other than four numbers, X, Y, Z, T. That doesn't help us a lot. In spite of the difficulties, we are going to try and get a feeling for this geometry. As a first attempt at understanding, we shall proceed by analogy. Here is a segment and an equilateral triangle. And finally, a regular tetrahedron. Our magical blackboard enables us to draw in space. How can we keep this up in 4 dimensions? Observe that the segment, the triangle and the tetrahedron have 2, 3 and 4 vertices respectively. Therefore, we can try to continue with 5 vertices. Let's go then. For the segment, the triangle or the tetrahedron, an edge connects each pair of vertices. So we have to connect the 5 vertices in pairs. We count 1 edge, 2, 3, 4, 5, 6, 7, 8, 9, and 10 edges. In the tetrahedron, there is a triangular face for each triple of vertices. We proceed in the same way, which gives us 2, 3, 10 faces. But if we keep going, by analogy, we have to add a tetrahedral face for each 4-tuple of vertices. There are 5 of them. That's it. We constructed our 4-dimensional object. We'll call this the simplex. Let's spin it around in space a little, as we did with the tetrahedron. Of course, you have to imagine the simplex spinning in a 4-dimensional space. What you see is only its projection on the blackboard. touch complicated is that faces get tangled and they can cross each other. Well, some experience is required to be able to see in dimension 4. We're going to take the simplex, which is in 4-dimensional space, and move it gradually so that different cross-sections of it meet our 3-dimensional space. In the same way that reptiles could see a polygon appearing and disappearing, we will see a 3-dimensional polyhedron which appears, changes shape, and then vanishes. Here is the simplex passing through our 3-dimensional space. We're now going to meet more 4-dimensional polyhedra, passing through our own 3-dimensional world. Here is the hypercube, a member of the family that starts with the segment and continues up through the square and the cube. It has to be said that getting a feeling for the geometry from the slice method like this is rather tricky. I discovered the analogues of the icosahedron and the dodecahedron. They have complicated names, but I'll just call them 120 cell and 600 cell, since the former has 120 faces and the latter 600. Look at the 120 cell. It's just passing through our space. And now here's the 600 cell. Of course, when I say that a 4-dimensional polyhedron has 600 faces, I mean 3-dimensional faces. These 600 faces are 600 tetrahedra. As for the 120 cell, it consists of 120 dodecahedra. In a minute, we'll see how we can get to know them better. To observe these 4-dimensional objects with our 3-dimensional eyes, we can look at their shadows. The objects are still in 4 space, but they are projected on our 3 space, exactly like a painter might project a landscape onto his canvas. We've already done just this with the simplex. Here is the hypercube. Of course, it's spinning in space so that we can appreciate all the details. Notice, for instance, that the hypercube has 16 vertices. Here's a little newcomer. It's the most beautiful of my discoveries. An object that I call the 24 cell. It has absolutely no analogue in dimension 3. It's a purely 4-dimensional creature. I'm very proud of my discovery. Look how wonderful it is. 24 vertices, 96 edges, 96 triangles, and 24 octahedra. A real little gem. Here is the shadow of the 120 cell in all its majesty. A rather complicated majesty, you have to agree. Let's get inside and have a look at its structure. Look. "600 vertices, 1,200 edges. 4 edges start at each vertex. A completely regular structure. All vertices, all edges play the same role. It's a pity that the projection breaks the symmetry. Let's work your imagination a little. Imagine the object in 4 space in which a huge group of rotations permutes all these vertices and edges. The champion is the 600 cell, like a gigantic macromolecule with its 720 edges and 120 vertices, and 12 edges starting from each vertex. Our exploration of 4-dimensional polyhedra won't stop here, as their stereographic projections are bound to give us a better feeling for the geometry.